Welcome to calculus. You will master complex problems, but forget how to add. On this episode, Stevenson will demonstrate Welcome. Now that we have a vague idea of what limits are, please know that there are properties with limits that help make our life a little bit easier. So by applying 6 basic facts about limits, we can calculate many unfamiliar limits from limits we already know. For example, if I know that the limit of a constant as x approaches c is a constant, and the limit of x as x approaches c is just c, so this is the identity function, this is a constant value, we can calculate the limits of all polynomial and rational functions. And this idea is listed in the properties. So you have these written down. If not, pause and get these down. So basically just some elements here. L and M, capital L, capital M, just represent the output of each limit. So the limit as x approaches c of f of x will be represented by L, and the limit of g of x as x approaches the same one, c, will be M. And so c and k just represent real numbers, and they are just arbitrary constants in that sense. So there's the sum rule. What this says is if you have the limit of a sum, then you can just add up the individual limits together. Okay, so the limit of the sum is the sum of their limits. Now, the difference rule. Difference rule is the same idea of the sum rule. So if I have the limit of a difference, I can just subtract the two limits values individually and I get the same result. Product. If I do the limit of a product, I can just find the limits individually of f and g and multiply them. Constant multiple rule. This is kind of an odd one, but basically if you know your function has a constant in front of it that is being multiplied, you can actually take the constant out of the limit, find the limit, and then just multiply it by the constant. So that doesn't get used too often, but later when we do more complex derivatives and antiderivatives, this idea of constant multiple rule will come up a lot. Quotient rule. If I'm finding the limit of two functions that are being divided, I can divide their limits individually. However, huge requirement. The limit of the denominator function cannot be 0. Why? Well, can't divide by 0, right? So, power rule. This one's a little bit interesting. I don't see this too often, but essentially if you want the limit of some function being raised to a power, you can find the limit of the function itself and just raise that value to a power. Okay? There's also another kind of property. It's called, or it's more of a theorem. So those were properties. Here's theorem 2, polynomial and rationals. Because the way these properties work is, remember I said you can find limits through graphing or by tables. But we're going to do a lot of things analytically. What does analytically mean? Analytically means, unless it is otherwise stated, everything will be used without the use of graphing calculators or any sort of technology. So, if you know your function is a polynomial or is rational, you can find the limit by direct substitution. So, here's how that works. Look at this example right here. What is the limit as x approaches 3 of x squared times the quantity of 2 minus x? Now, we can't use technology, so we can't graph it and look at the picture and figure out where is it approaching 3, or when x approaches 3. So, we look at our identification, we go, wait a minute, this is polynomial, right? If I distribute the x squared, I'm going to get a cubic function. So according to my theorem here, it says if I have the limit of f of x, and I know f of x is any polynomial function, then all I have to do, the limit equals the function evaluated at what x is approaching. That's what this says. So let's look at it. X is approaching 3, so all I have to do is plug 3 in here and here. And then I do order of operations, and I get my answer. Now, rationals follow a similar path. This is a rational function. I'm asking for x as it approaches 2. Now, be very careful. Remember with rationals, we have to check the denominator for any discontinuities. But if I have x plus 2, my discontinuity is negative 2. Okay? So in this case, x cannot equal negative 2. But what is x approaching? Positive 2. So it's totally safe to plug this in. So I recognize this as rational, and so it says, in this particular case, all I have to do to find the limit of this, notice f of x is polynomial, x squared, g of x is also polynomial, x plus 2. So all I have to do is evaluate the function up top at c and the bottom at c. So I'm approaching 2 here, so that's my c value. So I'm going to evaluate the function up top at c. So I plug 2 in here, and then I evaluate the function at the bottom with the same thing. Simplify, and there I get it. So most polynomials, okay, as with most polynomials, the limits of many familiar functions can be found by substituting at points where they're defined at. This includes trig functions, exponential, log functions, and compositions of those. So make sure you're using those properties as much as you can. So I wanted to give you a couple demonstrations on how this works too. So let's look at the first one. So this is from the textbook. So 56 says that assume that the limit of f of x as x approaches b is 7, and the limit of g of x as x approaches b is -3. Now it's super important that when you're using these properties, the limits, the functions can be different, but the x values must be approaching the same value in order for these properties to apply. So get my fancy pencil here. All right, so let's look at the first one, A, right here. So this is that sum rule. So since I'm finding the limit of the sums, I can break them up individually like this. So the limit of the sum is really just the sum of the limits themselves. So I look up here and go, okay, well the limit of f of x was 7, and the limit of g of x was -3. So if this is multiple choice, I'm going to look for my correct answer. If it's free response, I stop. But to simplify for multiple choice reasons, I could see the answer is 4. Now, let's look at C. So this is that constant multiple rule. So this is asking for the limit of 4 times g of x as x approaches b. So I can rewrite it with the 4 out front, just like that. So this means I'm going to do 4 times the limit of g of x. So I go over here and I look and see the limit of g of x as x approaches b is -3. So this becomes 4 times -3. So this is -12. All right, let's keep going. Part B. This is the limit of the product of f of x times g of x as x approaches b. So my product rule says I can break up the limits individually. Just like that. So again, I look up here, the limit of f of x is 7, and the limit of g is -3. If it's free response, stop right here. For multiple choice reasons, let's simplify. 7 times 3 is -21. Last but not least, my quotient. Now, my quotient rule told me if I'm doing the limit of a quotient of a polynomial function here and here, then I can just divide them individually. But do you remember the one main restriction though? The one caveat. The denominator, the limit of the denominator cannot be 0. So I'm going to first rewrite this as the limit as x approaches b of f of x divided by the limit as x approaches b of g of x. That's what this is telling me I can do because of my properties. Well, what was the limit of g of x? -3. It wasn't 0, so that's good. This means I can continue on with what I'm doing. So the limit of f of x as x approaches b is 7. And the limit of g of x, I'm going to say that's not equal to, is -3. And that would be my answer. Leave answers improper. Do not change them to decimals or mixed numbers. Leave them just like that. So here's another example that I wanted to show you where you're not really using the properties, but you're using some of the I think it was the rational or polynomial theorem that was in the textbook. So I'm not going to cover those two. That's why I've scribbled them out, so don't worry about those. This is the one I want to look at. So the first thing what we said was that if we have something that is polynomial on the top and bottom, then we know we can directly substitute. But remember the caveat or the requirement was if I directly substitute and I create 0 on the bottom, that doesn't work. So let's test it. So if I plug 2 in the bottom there, I'm going to get 0, aren't I? That's a problem. So what we want to do, it doesn't mean we can't take the limit. We're going to simplify it. So this is where all your skills leading up to this year right now are going to matter. So we're going to factor. Yay, factoring. So let's review our factoring skills. So first times last, middle for the bottom. So my product is positive, but my sum is negative, which means they both must be negative. So what multiplies to give you 2, but adds to give you 3? Answer, 1 and 2. So this factors as t minus 1 and t minus 2. So actually, we're not going to simplify. We're going to rewrite it. Rewrite fraction. So this becomes the limit as, whoops, not x, this is a t. T approaches 2. So the numerator becomes this. So we have t minus 1 and t minus 2. The denominator is also factorable. That should be slapping you in the face right now. That is a difference of squares. T plus 2, t minus 2. Now, hopefully you recognize that actually, let's get rid of the limit notation. I don't want to do that yet. I want to make sure I'm properly working on this. So I'm going to rewrite and simplify down this fraction here. So hopefully you recognize, do you choose these two quantities, simplify. They don't cancel, they don't go to 0, they simplify to 1. So what I'm left with now is t minus 1 over t plus 2. Now I can safely apply my limit. How do I know it's safe to do that? Because if I take 2 here, because that's what t is approaching, and I plug it in, I don't get 0 in the denominator. So let's do that. So what this equals is this equals 2 minus 1, 2 plus 2. 2 minus 1 is 1, 2 plus 2 is 4. So when you have rationals, always test the denominator first. Make sure you don't get 0. If you do, not a big deal. Try to simplify it using factoring techniques. Reduce it down. At this point in our year, it will be reducible at some point. There will be things later on where it's not reducible, and I will teach you how to approach those then. Good luck.